Next up, Alex Blunder gives us an insight into file format fuzzing in Android.
Okay, hello, thank you for the nice introduction. My name is Alex Blunder. I work as a software security engineer for Intel's Open Source Technology Center in Romania. Today's talk is focused on an approach that can be used for performing file format fuzzing in Android. These are the main points of the presentation. First, we'll see a general overview of how we can perform file format fuzzing in an Android environment. Then we'll see how this approach can be applied to several targets from the Android operating system. We'll see how to perform fuzzing against the Stagefright media framework and also the Android application install process. Towards the end of the session, we'll also see how to use an alternative approach, more exactly how to make use of the American Fuzzy Loop tool, which is a very popular fuzzing tool, in an Android environment. So for the general fuzzing approach, these would be the steps that can be taken in a testing campaign. First, we need to figure out how to generate the malformed data for our different fuzzing needs. The actual execution or the running of the test cases won't be taken into consideration for this general approach, because this would be a step that is highly specific for each target. So I'll discuss more about this for each project example. After generating the data and executing the data on the device, we need to figure out a way to actually see what's happening with our testing campaign. So to monitor the results, we need to figure out a way to do this in real time. So we'll be talking about a logging process and how to develop a logging process that can be applied to general scenarios. In the fortunate case when we have a fuzzing campaign that generates good results, so we have, let's say, a large number of crashes, we also need to come up with a way to uniquely sort them. So we need to figure out a way to develop a triage mechanism. So we've generated the data, we've executed the data on the Android device, we've monitored the results, we saw what happened there. We've sorted out the unique issues, and now we are left with a small number of unique issues that need to be analyzed. So I'll be also talking about a few methods in which we can achieve this task. Generally speaking, in fuzzing, and more specifically in file format fuzzing, we can have either mutational fuzzing or generational fuzzing. Mutational fuzzing means that we have an initial set of valid files that can be fed to that target application or the target system component, and we try to malform it or to corrupt it in various ways. It's important to note that we must try to maintain the structural validity of the file that we are fuzzing, because we need to have the component that we are targeting believe that the input that we are feeding it is actually valid. So the target would actually accept that input and parse it and maybe give a crash. In generation fuzzing, on the other hand, we try to create the malformed input from scratch. In this case also, we need to be aware of the structure or the format of the input, because we need to know the way in which we can construct that test case. The tools that we have been using for our fuzzing purposes in Android are the ones mentioned on the screen. The first one is the basic fuzzing framework. This is a tool that can be used in Linux environments. It targets applications or binaries that consume file input. The thing is, the main advantage for this tool is that it is almost completely automated. So it generates the GDB traces and the Valgrind traces for the crashes that it finds. It also tries to do a best effort into sorting out the unique issues so you don't have to actually develop a triage mechanism if you run the tool in a Linux-based environment. The tool is actually based on another popular tool, so it's based on a modified version of Zuzuf, which is also a general-purpose fuzzer. Another tool that we've been using is a smaller one, Fastbox. This tool is specialized on multimedia codecs. We've been mainly using this tool for fuzzing the Stagefright media framework. It also runs only on Linux environments. Redamsa is another popular solution. The main advantage for Redamsa, and the reason why we used it, is because you can pass a seed to the tool, and you are able to quickly reproduce a test case when you find that a specific test case has produced a crash or an issue. The American Fuzzy Loop is probably the most popular fuzzing tool at the moment. I'll be talking about it in more detail in a section of the presentation. It can be really considered to be either a mutational or a generational fuzzing tool. It's more like an evolutionary fuzzing tool because it's based on the response that it receives from the application based on the coverage. So let's say we have a fuzzing campaign and we've generated the data using the tools that I've mentioned. We need in Android a way to figure out what's happening with our test cases. So if you're familiar with Android, you are also familiar with its logging system, so the logcat buffer. The thing is that each time fatal crash occurs in Android, so each time a crash occurs at the native code level of Android, a fatal message is generated and inserted into the logcat buffer. The logcat buffer gathers messages from all types of components from the Android OS, including applications, and assigns them different priorities. We have in total 7 priorities, things like fatal messages, error messages, information messages, debug messages. And you can actually sort the logcat buffer to print out only messages that have a specific priority. So what we do in specific fuzzing campaign, for each test case that we send and execute on the device, we also artificially insert a message into the logcat buffer. We can do that using the log command that is built into an Android device shell. We can specify the priority of the message, the component with a tag, and other information about the test case that we are executing. So this is an example of a general template for a fuzzing campaign in Android. So each time we execute a test case on a device, we also send a message with a fatal priority with information such as test case index and, more importantly, a way to actually reproduce the issue. In the case of fuzzing media files, for example, if we are fuzzing or if you are corrupting the media files locally on the Linux machine, we can save all the files that are being modified, and then for the reproducibility issue, we can only have, let's say, the file name that is sent to the device. This would be a simple example because in order to reproduce the crash, we can just go on the local machine where we have all the test cases saved. So for each test case that is executed, we also insert a fatal message. And when an actual fatal message or a crash occurs and the system generates this type of message, we will know that the test case immediately above it is responsible for the crash. However, if we have a large number of devices that run for large periods of time, there are chances that the logs will get very crowded. There will be a large number of crashes, and we will simply can't go through them manually and start to look, oh, we have a segmentation fault, let's look at this test case, try to reproduce it, and see what's going on. So you have to come up with a way to actually take the logs that are parsed after a testing campaign and go through them and automatically find out which of the issues are unique. We can do this by developing a triage mechanism. So besides inserting a fatal message into the lookup buffer, each time a crash occurs into the native code level of Android, we also get an entry here in data tombstones on the device. So a tombstone file is generated each time a crash occurs in Android. This is what the tombstone file looks like. It contains a lot of useful information about the crash. So we have the signal and the code for the signal, the process that crashed, the fault address, the registry values at the time of the crash, and the backtrace for that crash in the targeted component. It contains actually a lot more information, but for the purpose of the triage mechanism, these are the information that we need to look at. How can we uniquely identify a crash based on this information? By looking at this value, the program counter value, where the crash occurred. So this value is unique for each crash that occurred in the same process. However, we need to be careful of how we apply this mechanism, because if we have two identical crashes, but the image that is built on two separate devices is different, then the program counter value will also be different, although the crashes are identical. So we need to use the triage mechanism when working on a cluster of devices that have the same image flashed onto them. How does it actually work? So how do we actually implement the triage mechanism? So we have the logs from the actual testing phase. We take those logs and we start to parse them. We identify the fatal messages. When we identify the fatal messages, we also have the actual test case that produced the crash. In some cases, it's simpler, like in the case of media files. In other cases, we just take the reproducibility info. We try to re-execute that input that caused the crash to try to confirm that the crash actually occurs. And if it does occur, then certainly a Tombstone file will be generated. Then what we do is we take the Tombstone file, we parse it, we get the program counter value from the backtrace, and we check if the program counter value has been previously encountered. If it has indeed previously been encountered, then it means that the crash is not new. But if the PC value is new, then we consider it to be a unique issue. We save the tombstone, so we have information about the crash, and we also save the input or the reproducibility information, so we have a way to actually reproduce that crash. So let's say we had a large number of crashes. We passed all the crashes for the triage mechanism and we are left with 2 or 3 unique issues. What can we do next? So what can we do to try to analyze and find debugging information? The first place we go is, as I mentioned earlier, the data tombstones location, where we have the tombstone that is being generated. The actual signal and the signal code can give us the first type of information that can be useful into determining the severity of that crash. Also, the fault address is important, and the registry values. We can also take a look at the message. You have on the screen 2 examples of actual crashes in the Stagefright media framework. The first one is an error 4, and the second one is an error 6. The first one is an user mode read access fault. You can see how the error codes can be formed. So we have a 00100, and the second one is on write access user mode fault. You have 01100. This also can give us some information about the crash. Moving on, we can also use GDB to perform debugging in Android. For this, you first need to enable GDB server on the device. You can do this in 2 ways. So either you can attach GDB server to the process ID that you are trying to debug, or you can actually, if the process that you are targeting can be started using an executable or binary, you can actually start it already using GDB server. You need to mention the port. So this is done in the shell of the Android device. Then you go onto the local machine where you have the Android device connected, and you forward the TCP port that you use to start the GDB server. You start GDB regularly. You start a remote debugging session using this command and mentioning the port that you have used. And all you have to do is just resume the process execution. It's important to note that if you really want to have a meaningful debugging session, you should also use the debugging symbols that can be taken from the Android tree after you have built an Android image and actually flashed it on the Android device. In the fortunate case when you actually have access to the source code of the component that you are targeting, in Android, in most of the cases you do have, but there are some binaries that are proprietary and you don't really have access to its source code. You can use address to line. You take the backtrace from the data Tombstone files and you check the program counter value for the component that you are targeting. We are not really interested into seeing the line of code where the crash occurred into libc. We are more interested in actually seeing what happened inside libstagefright, so the last call from the libstagefright library. Then all you have to do is pass this value as a parameter to address to line. You also need to have access to the symbols of the image that you have built and actually have that same image that you are passing the symbols here flashed onto the device, so you have the right correspondence. Okay, so I'm going to move on and see how this applies to the first project example, which is fuzzing the media framework in Android, more specifically Stagefright, which has been a very popular topic in the Android security world. First, why are media files attractive vectors? There is the fact that, generally speaking, audio and video files are binary streams that contain complex data. There are a lot of specialized components that handle the parsing of these files, and because of that, there is the probability that when parsing these files, memory corruption issues may occur. Then there is the fact that it is a very large attack surface, so really people who are trying to find ways to actually find bugs and exploit them have a lot of possibilities in doing this. There is also the perception that media files are harmless, so users, normal users won't generally have second thoughts when downloading or using media files from untrusted sources, especially because these media files can be played without the actual consent of the users. It's the example that made the Stagefright bug very popular, the one that where an MMS message is sent that has a media file attached to it. And in Android, there isn't really a way to give special permissions when playing or downloading media files, which is also an attractive point from an attacker perspective. So this is what we've tried to achieve. So we have an initial set of valid media files, so we perform mutational fuzzing against the Stagefright media framework. What we do is locally, so not on the Android device, we create malformed media files that we try to keep structurally valid. We direct the test cases that are created locally to the Android devices. More specifically, we are directing the test cases to the Stagefright media framework, and we'll see how we actually do this. We monitor the system for potential issues using the logging process approach that I've mentioned in the first part of the presentation. And then because in this case we had really a large number of crashes from the beginning, we had to come up with the triage mechanism, and we passed the results through the triage mechanism. In the initial phases of the project, we had to figure out how to actually send the test cases that we were fuzzing to the appropriate decoders. The first solution that we came up was to just play the corrupt media files inside different media player applications that are available on Android, or to leverage the Java API that handles media playback. However, the best solution that we came up with was using the Stagefright command line interface, which can be optionally built into an Android device from this path in the Android tree. The main advantage is that using this command line interface, you have direct access to the native code of the media framework. So you bypass all the Java layer, and which would impose an unnecessary performance overhead, and it would be possible also that some of the issues would not reproduce because the test cases won't get parsed, would get parsed only in the Java layer. These are some of the main functionalities of the binary that can be built into the Android shell. The functionalities that are of interest to us are the fact that you can pass an audio or a video file to be decoded. So it can actually take input media file and direct it to the appropriate extractor for the appropriate file format. You can also force the playback functionality for audio files, and also force the usage of a software or a hardware codec. We've tried to, for each test case that we have sent onto Android devices, we tried to test to see if anything happens using both software and hardware codecs. Another interesting functionality is the fact that you can extract the video thumbnail, so crashes can also occur when the image files that are associated with video files are being parsed by the specialized components. So this is how an actual log looks like, a log that is being created using the template that I've mentioned before. So for each test case that is being generated locally, we send it onto the device and then pass it as a parameter to the Stagefright command line interface. Each time we do this, we also insert a fatal message into the lockout buffer that looks something like this. So we have the component that we are targeting, and as I mentioned earlier, just the file name of the media file that we have created. This is the simple example where all the test cases are also being saved onto the device. So when an actual real crash occurs, like this one here, we'll know that this file is responsible for the crash, and we can just go back onto the local machine, get that file and try to reproduce it. These are some of the results that we had with this fuzzing campaign. So we've started this project sometimes in the beginning of 2014. In the first weeks of running the fuzzing campaigns, we had extremely surprising results because the Stagefright media framework would just keep on crashing. That led to the development of the triage mechanism, so it was actually a necessity because we couldn't just go manually through all the crashes that we had. The first severe issues were reported to Google and assigned CV issues in September 2014. These were integer overflows in the live Stagefright libraries. These are bugs that are very similar to what is commonly known now as the Stagefright bug. We also open sourced our tool that made possible the discovery of these issues in February 2015. So the tool is publicly available on GitHub. You can take a look at it. But actually we are not really using it for its initial purpose. So we are now using it as a complementary solution alongside with the American Fuzzy Loop tool. I'm going to explain a bit more about this in a following section of the presentation. This is the second example that I'm going to talk about. It relates to fuzzing the Android application install process. First, why is this important? There is the fact that the component that handles the application install in Android is a process that runs with high system privileges. So any issue that is found here and can be exploited by an attacker can have a greater severity from a security point of view. There is also the fact that installing an application is one of the few ways in which an unprivileged user, so an external user, has access to send input to a privileged component in Android. Also, fuzzing in general gives issues that are not generally found through regular validation. This is also the case here because issues that we can find through this methods would not be found through regular validation. I'm talking when we have an APK that is trying to enter, let's say, the Google Play Store. These type of issues won't be found through the validation that is performed before entering that market. We've identified two approaches that can be used. The approaches are different because the newer Android versions have switched the Dalvik virtual machine with the Android runtime. So going through all the steps that are taken at the system level to actually install an application onto the device, we found that the most interesting components from a fuzzing perspective would be in the case of ART, the dex2out component, and in the case of Dalvik, the dexopt component. The dex2out takes as input a dex file, which is the compiled Java code from an Android application, and converts it into an OAT file, which is actually an executable, so an ELF file. In the case of KitKat, the process is similar, only that dexopt takes input a dex file and converts it into an optimized dex file. This would be the testing process overview. So this is also a mutational fuzzing process. We have large amounts of initial valid APK files. An APK is actually the application file that contains the Java code and the native library code. So we have the initial APK valid files, and for each APK we unzip it. We extract the components from the APK because basically an APK is just a regular RHAV file, and we fuzz the APK components that are of interest to us. And then in the case of Dalvik, we repackage the APK and send it to the Android install process. And in the case of ART, the things are more simpler. We can actually parse, we can actually send different components directly to the install process. These are the components that are regularly found inside an APK. So the components that are of interest to us is the classes.dex file, which is the compiled Java code file. This is the actual file that we will be fuzzing. Another alternative target for fuzzing could be the Android manifest file. However, this was not in the scope of this project. The meta-inf folder contains the signing information for the APK. This is also a component that is of interest to us because, for example, if we have an initial APK that we extract its components and start to modify things in it, and then we try to repackage it and reinstall it onto the device, that won't be possible because the signing information won't allow this. So each time we modify an APK, we need to actually re-sign it so we can install it onto a device. Because the approaches are different on Dalvik and ART. I'll start with the one on Dalvik. DexOpt is a binary that exists on the device, so it's located in system/bin. However, we can't use it directly, so we can't call it directly because it takes a lot of parameters that can be obtained from a shell-like environment. So what we thought is to actually simulate the entire APK install process. These are the actual steps. What we do is for each APK, we extract the classes.dex file. We fuzz that file. I'm going to talk into detail about how we actually fuzz this. For the moment, I'm going to mention only that we will fuzz the dex file. We remove the original file from the initial APK. We repackage the APK with the modified dex. We need to create a local key store so we can be able to actually sign the APK. We can do this with the key tool command. We remove the previous signing information by removing the metainf directory, and we reassign the APK using our local key store so we can actually install the APK. This is a log example that was taken from an actual fuzzing campaign against DexOpt. So we can see here that for each APK that we are testing, we have the APK ID, the initial APK, and the seed for Radamsa. What we do is we don't save each malformed APK that we are testing against the device. We only keep the initial APKs and the seed that can be used to actually reproduce the issues. So this seed that is passed to the Radamsa fuzzer is used to actually fuzz only the classes.dex file and then repackage and sign and resign the APK. This is an example of an actual crash which was generated by this APK ID with this seed. In the case of ART, so in the case of DexOpt, things are more simpler. We can actually directly use the DexOpt binary. We use it by passing a dex file like this and a resulting OAT file. So what we have to do is we have the initial APK valid files. We extract all the classes.dex files from them, and then we start fuzzing only the dex files and sending them as parameters to the dex2out binary. This is the log example. This is how it will look like. So we don't have the APK, we just have the dex ID. The principle is similar with the one mentioned at DexOpt, because we fuzz also using Radamsa and by passing a seed to the fuzzer. The thing is that the Android system has in place an install verification process that checks if the dex files we are trying to install are actually valid. So when we first started the project and did completely random fuzzing and tried to install applications, we mostly came up with error messages like this one, because the system was able to figure out that the dex files that we were trying to install were invalid. This is bad for us from a fuzzing perspective, because we want the component that we are targeting to actually parse the input that we are feeding it. And this wouldn't be possible if the component rejects the input from the beginning. To overcome this, we've considered 3 fuzzing methods. The first one was the initial one, where we completely, when we performed a completely random fuzzing campaign against DexOpt. This couldn't actually be applied to DexOpt, only to DexOpt. Then the second method was do a partially guided fuzzing, where we would random fuzz the dex file and then come back and try to fix as much as possible into the file header. And then we had the targeted fuzzing, which was pinpoint an exact section of the DEX file, fuzz only that section, and then have more control of what were the things that have changed, and have more control over the header sections that we can modify. This is the DEX file format. I'm not going to go into very much detail. What you need to understand is the fact that the header contains first general information about the file, things like file size or checksums and header size, and then specific information about each section, more exactly the offset and size of each section. This section contains the actual content of the compiled Java files. This is the optional field. It also contains information about the offsets of the section and what is the type of content that is present in the section. The partially guided fuzzing approach, we took the DEX file as a whole and started fuzzing randomly things inside it. Then we came back, took a look at the header, and tried to fix as much as possible. We have the magic number in the header, which is a constant, and also the header size and the endian tag. So if by accident we would have modified those values, we would come back and rewrite those values. We could also recompute the checksum and the SHA-1 signature and the file size, because after different modifications, these values would be different and invalid. So this was the first approach. The second approach, we would take the file, split it in three. The section that was of interest to us was the data section, because it contains all the strings and all the variables that were used by the Java methods. We would fuzz only this section, glue back all the chunks together, and try to fix the header. Besides the sections that we would fix in the first approach, we would also have information about the map offset, because the fuzz data section could be bigger or smaller, so the offset would change and we would know exactly what would be the offset, and also the data size, because we modified that could also be variable. This was actually the approach that gave the best results, and I'm going to explain a bit about that later. The approach that we've used in the beginning was to actually take large amounts of DEX files, valid DEX files, fuzz them randomly, and don't check back with the header, so just send them against DEX2out. This was surprisingly an approach that also gave some results. So although the number of crashes was not as spectacular as in the case of the Stagefright Media Framework fuzzing campaign, we had initially about 1,000 crashes, not unique crashes per week, on a cluster that ranged from 20 to 30 Android devices. There was also a critical issue discovered. This was discovered in November 2014. Google assigned the CVID for it. There are also a number of low priority issues that affect both KitKat and Lollipop that are now fixed. The project is still going, so there are still a number of issues that are currently under investigation. This is the last section of my talk. This is an alternative approach using the AFL tool. So the American Fuzzy Loop is a fuzzing tool that is developed by Michal Zalewski. It offers two fuzzing modes: the dumb mode, where it performs actually completely random fuzzing, and the instrumented mode, where you have to instrument the binary that you are targeting. So you can actually detect the changes to the program control flow and try to direct the code paths that you are accessing. It has the advantage that it detects both crashes and hangs and tries to sort them to offer only the unique issues. We had an Android port of the tool developed by a colleague of mine, by Adrian. The patch is also publicly available now on the mailing list of the tool. You can check out the link in the presentation. This is how we used, and we are still using, AFL alongside with our custom-built Fuzzer to perform fuzzing campaigns against the Stagefright media framework. So this would be the fuzzing flow. We have the seed generation phase, where we actually generate valid media files. We use this, we obtain this by leveraging the functionalities provided by the FmpEg tool. So if we, let's say, have an initial MP4 file, we can use FmpEg to convert that MP4 file to all sorts of codecs and containers. We generally try to cover all the container and codec combinations from the Android CDD. After generating the initial valid media files, we load the seeds onto the device where we run AFL. AFL, the version that is working on Android. We get the crashes and the hangs that are reported by the AFL tool, and what we do is pass them through the media fuzzing framework, our media fuzzing framework, in order to actually detect which issues are unique. Because first there is the fact that the test cases are executed on AFL in a constrained environment, so you have to set a specific memory limit and a specific timeout limit for the execution of the test cases. And in some cases, if AFL reported a crash, the crash won't actually reproduce in a normal usage scenario when actually passing it to the Stagefright command line interface. There is also the fact that there are AFL runs on a large number of devices. So if a crash is identified as being unique on one device, it is also reported as unique on a second device, but they are not actually unique in between. So we try to identify the duplicates between the results that are being reported on several devices. That is why we are using our custom fuzzer. So our custom fuzzer receives as input the crashes and hangs that AFL reported. It generates the logs, as we've seen. The logs are parsed and passed through the triage mechanism, where we are then left only with the unique issues. This approach also gave some results. So this was one critical issue that affects the Stagefright library. It was a heap corruption, which could lead to arbitrary code execution in the media server process, which is a process that has some special privileges. This was discovered in August 2015 and was included in the first public Nexus security bulletin. There are also a lot of multiple low priority issues that have been reported to Google and are now fixed, mainly null pointer dereferences or stuff like integer division by zeros issues. Some conclusions. First, there is the fact that fuzzing inside an Android environment would be a little bit more tricky than in a regular Linux environment. Then, although Stagefright has been highly publicized, has been a highly publicized issue lately, it's important to understand that it's not actually a bug, so Stagefright is not a bug. It's more actually a library that has a lot of issues. Also, when performing fuzzing, it's important to understand the internals of the system that you are targeting. You could try to perform intelligent fuzzing, or just get lucky with performing completely dumb fuzzing. And that would be kind of all. If you have questions.
Thank you. Okay, questions? Okay, I guess everyone is quite hungry already. Well, thank you very much.
I have a question here.
The testing that you're doing on the Android devices, are you using physical devices or are you using any kind of virtualization?
No, we are using clusters of actual devices. Mainly we are testing on x86 devices, so Intel-based devices, and we are trying to see if the issues reproduce on ARM or are just specific to Intel devices.
Okay, thanks.
Well, thank you very much for your attention.
Thanks.
And lunch is downstairs. Enjoy.